Hey, good morning, everybody. If you don't have your exam, please drop by and see me afterwards. I'll give it to you. We have a OpenStax assignment due on Tuesday, I think, right? I make it Tuesday? Is it Tuesday? Monday. What? What did you say? What?
One's Monday, one's Tuesday.
Yeah.
The reading is Tuesday.
Whatever. So if you working on those, who's finished them already? It's like the four of us. We should get together. We should go out and have burgers or something. Because we don't have anything to do. And then everybody else has to go to the library and work on their own. But do that, please. I think that you'll find those problems are easier. Did y'all find them easier than previous assignments? And you know, I think that in general, this chapter, it's not easy, but I think it's easier than previous chapters. So that's good news for y'all. I want an awesome home run on the next. Okay? Let's do some questions. No help session today. I just sent y'all a message. I'm sorry about that. I have another thing at 2. If you go to the back of your book, this question addresses our potential energy. We usually allow the ground level to be our y equals 0, but you can let your y equals 0 be anywhere you want it to be. And so usually when we talk about potential energy, we talk about changes in potential energy. And this question is just sort of addressing that. That looks like a snowboarder, not a skier, right? All right, let's stop in about 10 seconds, 125. Okay, let's see here. Do we agree on the skier's potential energy? And remember, we have 2 people working this problem, and say one person would say that at the bottom this is y equals 0, and another person might say that up at the top that this is y equal to 0. And so we have 2 different people working this problem, but they're setting their y equals 0 to be different at different points. But you can do that. There's nothing wrong with that. You can set your coordinate system wherever you want. And so, for example, this person is going to set the skier's potential energy to be 0, because this person says, oh, this is y equals 0. Whereas this person will set the skier's potential energy to some non-zero value. By the way, when the first person, that is the one that's working it in this way, when the skier gets down to the bottom, what's going to be true about the potential energy of the skier? Is it positive, negative, or 0? It's going to be negative, right? Because his y position will be 0. If you're setting this to be 0, it will be negative. Then as you go down, your y position gets more negative. So they're not going to agree on A, the skier's potential energy, but they will agree on the change in potential energy, right? Because really all that's important there is this change in height. And so it doesn't matter where you set your y equals 0, they will agree on the change in potential energy. Will they agree on the kinetic energy at the bottom? Yeah, the skier is going to have whatever kinetic energy he needs or he has at the bottom. So E is the right answer. B and C is right. All right, 2 paths lead to the top of a big hill. One is steep and direct, while the other is twice as long but less steep. So one goes up like this, and then the other goes up like that. How much more potential energy do you gain if you take the red path? All right, let's stop at 55. 55. Good job, that's right. You gain the same amount of potential energy. Your change in potential energy, delta PE, is going to be equal to mg times h, where h is just your change in y value. It doesn't matter if you take this more circuitous path, it's still going to have the same change in potential energy. And that results from what property of the gravitational force? What is a property of the gravitational force that causes this to be true? It's a what type of force? It starts with a C. Conservative. It's a conservative force. That means it conserves energy. And we also said that conservative forces are path dependent or path independent. They're path independent. They don't depend upon the path. And so the amount of energy that I gain in this path is the same as the energy that I gain in this path. Now, it takes more energy to take this path because you're losing energy as you go up along because of friction and what have you. But your change in potential energy is going to be the same. How does it work? Oh, we haven't got to this yet. Let me go ahead and give this to you, and I'll come back to it later. We're going to talk about the elastic potential energy. So you might just want to make a little note, and then I'll give it to you later. It's kind of important, but unfortunately it's not in the workbook, but I'll give that to you in just a bit. Elastic potential energy. This describes the potential energy of a spring, right? Like a rubber band. If I stretch it, then it has the potential for motion. And that elastic potential energy is given by 1/2 kx squared. K is the spring constant. Y'all play with springs a little bit. Or have you already? Have you already done springs in the lab? No, you will soon, where you have to measure the period of the spring. And you'll measure the spring constant. And then x is the elongation of the spring. I'm going to say the displacement of the spring. That is how much it's stretched or how much it's compressed. The spring constant describes the stiffness of the spring. A more stiff spring has a higher spring constant. X describes how far it's stretched out or how far it's compressed. So if I do work on a spring and I stretch it 2 centimeters, how does that work compared to the work required to stretch it 1 centimeter? Now remember our work energy theorem, that work is equivalent to our change in energy. So I stretch it 2 centimeters, how does that compare to stretch it 1 centimeter? Stretch it twice as much. Okay, let's stop at 45. 45. Good job. Y'all are awesome. Hey, what do computers eat for a snack? Microchips. Oh, that was a good one. Okay, so C is right because potential energy, elastic potential energy is 1/2 kx squared. If I double x, which is what I've done, I've gone from 1 centimeter to 2 centimeters, I quadruple the potential energy. It's 4 times the amount of work that's required. Okay, you attach a mass to a vertical spring, it causes it to stretch and move downwards. What can you say about the spring's potential energy and the gravitational potential energy of the mass? I have a spring, then I attach a mass to it. What has happened to the spring's potential energy and the gravitational potential energy of the mass? All right, let's stop at 58. 58. All right, the elastic potential energy of the spring increases and the gravitational potential energy decreases. The elastic potential energy, we'll call it PES here, it goes up because X increases. But the gravitational potential energy, which we call G, goes down because H decreases. Right? PES, that's that 1/2 kx squared. PEG, that's our gravitational potential energy. That's that mgh, which is what we've seen already. That's the work that's done by the gravitational force that goes into potential energy for that object. All right, 3 balls of equal mass start from rest and roll down different ramps. All ramps have the same height. Which ball will have the greatest speed at the bottom of its ramp? I'll let one be A, 2 be B. Which is going to have the greatest speed at the bottom of its ramp? All right, let's stop at 43. 43. You'd think it'd be A, wouldn't you? But it's not, it's B. And we can think about this in terms of energy, that all the balls have a certain amount of energy at the top. And that energy is all potential energy, and it's equal to mgh. At the top, they have no kinetic energy. Kinetic energy is equal to 0. But at the bottom, they have no potential energy. Potential energy is equal to 0, and kinetic energy is equal to 1/2 mv squared. So you say, what happened to all that potential energy? Right? Isn't that what you say? Well, all that potential energy went into kinetic energy for each of these. All of these balls, their potential energy, when they go to the bottom, is converted into kinetic energy. And so we'll work through some problems where we can actually find the speed of these balls as they travel down the inclined plane. Now, we could have done this with chapter 4 and 3, the stuff that was down there, to find how fast does it accelerate down the plane and then go through our kinematics equations and figure out what is the speed when it gets to the bottom. But you'll see that by using the conservation of energy, it's much, much easier to figure out how fast the ball is going at different points. We did that a little bit last time. We'll do it more today. Okay? Yeah, MJ? Well, they're rolling, so there's just not much friction. Oh, I see what you're saying. Yeah, so if it was a sliding situation and you had friction at work, then which one would be going faster? If they were sliding down and friction was at play, which one would go faster? Right, one would go faster. That's a good question. Yeah, I'm sorry that wasn't clear about that. Yeah, a lot of y'all put A, didn't you? Okay. Let's do this one, and then maybe we'll go to the notes again. Truck initially at rest rolls down a frictionless hill. Speed of 20 meters per second. If we achieve a speed twice that, how much higher must the hill be? And listen, you want to think about this equation. The potential energy at the top is equal to the kinetic energy at the bottom. And ask yourself, what can I do to h in order to double the speed v? Right now, many of you are split between D and E. It is one of those answers. A few of you have A, B, or C, but it is either D or E. I want you to think about which it is. Is it going to be twice the height or 4 times the height? Write out that equation. You know what DE is, right? It's mgh. You know what KE is? That's that 1/2 mv squared. If I want to get twice the speed, what do I have to do to h? Okay. Let's stop at 140. 140. These are good test questions, by the way. Okay, E is the right answer. Look, whenever I encounter these, I like to write out the variables that are relevant. So I have mgh equals 1/2 mv squared. And I know that I want to double my speed. But if I double my speed, that means that over here that I have to have a factor of 4 in order to keep this equation balanced on either side. So that means that in order to get twice the speed, I need to go to a height 4 times as high. 4 times as high. Let's come back to this. We're going to do some more spring stuff, and we'll come back to this later. Okay. Let's work this problem. I have a video I want to show you. You all have plans for the weekend, by the way? Any big plans going on? Oh yeah, right. There's game tomorrow. What else? Work and homework. Yes. Because you have homework here for this class. You have a track meet or a cross country meet? Awesome. I think there's a 5K too on Sunday.
There's a buddy walk.
Oh, and buddy walk too. Yes. All right. We're not really doing that much. We have babysitting co-op with our neighbors, so we're taking their kids out this afternoon for dinner while they go do whatever it is they do on date night. Some friends of ours, the Holstoppels. You know Joseph Holstoppel in art? He's a painter, oil painter. No. His wife makes these little dolls. You can buy them on Etsy. You send her a picture of yourself, and she'll make a doll that's sort of made after you. But you know, they're very artsy and stuff. It's cool. She can make mobiles. If you want to buy one, let me know. I'll send you her website. But she's an artist too. But she's like, with cloth and stuff. What was I doing? Oh, this video. I don't know if it's real or not. It looks real, right? All right, so we want to know various things about this. First, we just need to sort of estimate some of the heights that are involved. And then also we need to estimate our mass. So we have a basketball goal. We have this woman. They take her, throw her up into the air, and then she comes back down again. I want to know a couple of things. I want to know what is the total energy at the top of her trajectory. So what amount of energy does she have up at the top? What is her velocity at the bottom of her trajectory? Right after she leaves the guy's hands, what is her maximum speed? And this will be her maximum speed at the bottom. And then what is her speed when she travels through the basketball? when she actually comes down and goes through the basketball hoop, what is her speed there? So we can make some assumptions about heights and what have you. Basketball hoops, what, about 10 feet, right? It's about 3 meters. Let's say it's 3 meters. And I think she goes up about twice as far. So let's say that she goes up almost 20 feet or 6 meters. And so we'll also need to know her mass. She's not a real big lady, so we'll say that her mass is about 50 kilograms. All right, so what is the woman's total energy at the top of her trajectory? Well, at the top of her trajectory, you want to ask, what kind of energy does she have? Does she have potential energy, or kinetic energy, or both? At the top, which of those does she have? Only potential, right? That the kinetic energy, since V is equal to 0, is equal to 0. So her total energy is going to be mgh. That's equal to 50 kilograms times 10 meters per second squared times h, which is 6 meters. That's about 3,000 joules. So she has about 3,000 joules of energy at the top. And then we also want to know her velocity at the bottom. We're going to work this problem much like we did with the roller coaster problem. Remember with the roller coaster problem we said, is the kinetic or the potential energy 0 or not 0 here? And so we've already said that up at the top that the kinetic energy equals 0 and the potential energy is at its max. What about at the bottom? What type of energy do we have at the bottom of the trajectory? Do we have potential energy? Only kinetic, right. Potential energy is equal to 0 because her height is equal to 0. Or not her height, but, you know, her y position. And the kinetic energy is at a max. It's equal to 1/2 mv squared. And so what we're going to do is we'll say at the bottom, Ke plus Pe is equal to Ke plus Pe at the top. And in these problems, which you're going to see several on the test in a couple of weeks, you'll approach them all like this, where you set the energy, the total energy at one point is equal to the total energy at another point. And as we said, at the bottom, potential energy is 0. At the top, kinetic energy is 0. And so this is going to be 1/2 mv squared is equal to mgh. Notice that our m's cancel, so we can divide through by m, and then we can solve for v. So v is equal to the square root of 2gh. What did I do there? I multiplied both sides by 2 to get rid of the half, and then I took the square root of both sides. The square root of 2gh, that works out to be about 11 meters per second. Okay? These are good test questions. You'll certainly see some questions like this. And if you look back at the old test, you'll see some similar things too. All right, and then let's look at 3. I want to know what is her speed when she goes through the hoop. What we're going to do is we'll take the total energy, say, at the bottom, which is all kinetic energy. There's no potential energy at the bottom. And set that equal to the potential plus the kinetic at the hoop. And we worked a problem similar to this last time with the roller coaster, that at particular points that you have, sometimes you have both potential and kinetic energy. And so here we would say 1/2 mv squared is equal to mgh plus 1/2 mv. I'm going to put a little hoop here to remind us that that's the speed at the top, or at the basketball hoop. Notice we can get rid of our m's. You'll rarely need the mass. We needed it here because we wanted to know the actual energy. But usually we're not even really concerned with how much energy the person has or the object has. Usually we're only concerned with the speed or the height of the object, in which case the masses will all cancel out. And then you solve this for v hoop. So I have half of 120, this is 60, equals 30 plus 1/2 v hoop squared. I think that's right. Yeah, h is equal to 3 meters. 10 times 3 gives you 30. Half of 11 squared is 60. And so this is equal to the square root of 60. Which is 8, 7, yeah, about 8 meters per second. Good test questions. Questions like that. You'll certainly see several that are very similar to those, where I give you a scenario. It might be a roller coaster, it might be a cheerleader thrown up in the air, it might just be some random object that's moving through different heights, and you have to figure out what is the speed of that object at a particular time. You have those in the OpenStax homework too, so it'll be good practice for you. Let's try it out, okay? Y'all try this one. Yeah, I might have used, did I use 9.8 for this one? Okay, yeah, I guess I did use 9.8, I'm sorry. Alright, let's go about 10 more seconds, say 225. Alright, B is right. So here, a lot like what we did before with the cheerleader, we have an object, we throw it up, it initially only has kinetic energy, that's going to be equal to 1/2 mv squared. It's going to go up to the top, and we want to figure out what is this height, h. But we know that all that kinetic energy is going to go into potential energy at the top. And so we say 1/2 mv squared equals mgh. I can get rid of some stuff, my masses cancel out, and then I solve for h. H is 1/2 v squared over g. And so that's equal to 1/2 of 225 over 10, which is going to be 11.5. Or roughly that. With 9.8 it was what? What? Okay, so it's a little bit different. Okay. Good example of a test question. I mean, this was on a test, but you'll certainly see something like that. Let's see. I brought a thing here. This is going to come up again when we do rotation in chapter 7, but I brought it here just because, you know, energy and all that. So this is a little loop-de-loop. Think about the energy that this object has. So, can y'all turn around a little? So, up here, the object has what type of energy? Only potential energy. And so if I let it go, that potential energy goes into what type of energy? Kinetic, right. Oh man, that was... You have to hold that level, and it's hard to hold the level. Right, so as it comes down, that energy will change into kinetic energy. Down here, it has what type of energy? Kinetic. And it has maximum value, right? But what about when it's here? What type of energy does it have? It has both. Okay, you want to see again? All right. So we have potential. It converts more and more and more and more kinetic down to the bottom. Then it gains potential and slows down, and then it comes back and goes down to the bottom. We'll look at this later because this is important to for circular motion and centrifugal forces and all that. So there's some cool stuff. But for now, we'll think about it in terms of energy. All right. Let's look at elastic potential energy. Hooke's law. You guys will get into this soon in the class. Hooke's law describes the force due to a spring. You've probably seen it before in chemistry or maybe even in biology. A lot of biological or chemical systems are approximated by Hooke's law. So you might have seen Hooke's law before and maybe not even known about it. But it says that the force from a spring is proportional to the displacement are also known as, aka I'll say, the elongation or the compression. So when I say displacement, I mean how much are you stretching the spring out or how much are you compressing the spring? And the force then is proportional to that. The way we would write this is we would say that F is equal to X, where X is this displacement. But then we also have a proportionality constant, and then we're also going to have a negative, and I'll explain what the negative comes about here. But X, this is our displacement. This is our spring constant. It describes how stiff the spring is. So, like your springs on your car, those have a big spring constant or a small spring constant? Big spring constant, because they're really stiff. What about the spring in your ballpoint pen? Big or small K? Small K. So, you know, next time you're taking those pens apart, do people y'all still take those pens apart? Because my kid takes those plastic pens apart, like whenever he can get his hands on them. And then he can never get them back right. But anyway, those have a small spring constant. And the springs on your car or other really stiff springs have a big spring constant. Okay, so that's Hooke's law. Now the sign, the negative, if you think of this spring system, notice you have, I've labeled all the forces on here. This spring is oscillating so that this is the equilibrium position. And a spring is always going to return to its equilibrium position because of the forces that are acting on it. But notice here that the force of the spring is towards the equilibrium position. What if I force this thing over here? What is going to be the direction of the force on the spring? Is it going to be to the left or right? Here it's to the left, but what if I go to the other side of the equilibrium position? What will be the direction of the force on the spring? To the left or right? It's to the right here, which is going to be on the other side of the equilibrium position. All right, let me draw a picture, much bigger I'll understand. So if I have my spring, we'll say that this is x equals 0, if I have a spring all the way out here, then it's going to pull in this direction, right? That's the force due to the spring. However, if I compress that spring, what is the direction of the force due to the spring? To the left or right? It's going to be to the right. That force, this is Fs here, this is Fs here. All right, so the force from the spring is always opposite the displacement. The spring wants, well, that's sort of an Aristotelian way of thinking about it, that the spring wants to return to its equilibrium position. But we're not Aristotelian, are we? We're Newtonian, not Aristotelian people. We're Newtonian, so we don't think of it in that way. We think of it in terms of the forces that are at work on this object, not that there's some natural state that the spring wants to be in. Okay, so conservation of energy also includes our elastic energy. And as I said, I've already given you this potential energy of a spring is equal to 1/2 kx squared. We can have a spring system, and you can certainly see one like this on the test, where you have a spring that's oscillating back and forth, and you need to look at and think about what types of energy that spring has. So at the different points. So like for example, right here, the elastic potential energy is 0. The elastic potential energy is 0 because x is equal to 0. It's at equilibrium. And the elastic potential energy is 0 because it's at the equilibrium position and x is equal to 0. The kinetic energy is also 0 because the speed is 0. But then I compress the spring. Now my elastic potential energy is at the maximum value. And the kinetic energy is 0. But then if I release the spring, it goes back to its equilibrium position, and like it shoots out this block, like the spring-loaded guns that y'all used in the lab when you shot the projectiles. Then all that potential energy goes in to the kinetic energy. We'll work a problem like this soon, where you have to use, just like the gravitational potential energy, but instead of gravitational, you're using elastic potential energy. If you're curious, you're not responsible for this, but this potential energy comes about in this way. You're not responsible for this, so write it down or not, I don't care. But it's, I care, but you know, you're not responsible for it. It's equal to the negative of the work, and it's going to be the integral of f dx. Y'all might have seen integrals in high school. Y'all don't take Calc 2, I don't think most of you. But you integrate f times the work, f dx, and this is going to be the integral of negative kx. That's f dx, which is equal to 1/2 kx squared. Well, that's actually negative 1/2 kx squared. Oh wait, no, I have a negative here, so it's positive. So that's where that comes from. You're not responsible for that, but that's where that expression for the potential energy comes from. The kinetic energy comes through a similar process. You have to integrate over some variables. And that's why you have that half and the squared term. All right. Now let's do this practice problem. This is similar to the one we've worked before, but instead of using gravitational potential energy, you're using elastic potential energy. So I compress the spring to this point, and then I let it go, and I want to know what is the speed at the equilibrium position. So I know the speed is going to be maximum value here because the potential energy is equal to 0. And so all the energy is now gone into kinetic energy. But what is the speed at that point? Don't forget that you need your elongation x that you needed in SI units. And it's given here as 20 centimeters. But 20 centimeters is how many meters? It's an important question. You need to convert your units. If you finish this and want to work ahead, next I'm going to ask, what is the speed at x equal 10 centimeters? So if you're already done, you can start looking at that. I'm going to stop the timer in about 10 seconds, 15 seconds. Stop at 255, 255. I think B is right. Let's try it out. I'm pretty sure B is right. Let's take a look. So on this one, we want to go through and just sort of think about what type of energy do I have. Right here, I only have potential energy. It's equal to 1/2 kx squared. It says that it's then released, so that means that it has no speed right here, so the kinetic energy is 0. Now over here, when the block is here, the potential energy, since x is equal to 0, that's equal to 0. And then the kinetic energy is now 1/2 mv squared. So we're going to set that 1/2 kx squared equal to 1/2 mv squared. All of my potential energy has become kinetic energy. Let's see, I can get rid of my halves there, and then I have to solve for v. So v is the square root of kx squared over m, which is the square root of 1200.2 squared divided by 1 kilogram. That's the mass. Is that 6.9? Anybody? Okay, that's 6.9. I'm pretty sure that's right. So that's how we work that problem. I take my energy at one point and I set it equal to the energy at the other point. That's conservation of energy. That your object will always have the same amount of energy. Now, let's consider this other problem. I don't have it as a clicker question, but it could certainly be a question on the test. What is the speed at x equal negative 10 centimeters? Or it could be positive 10. It would be the same process. It's going to be similar. I would say the potential energy over here is equal to the potential energy here, I'll say at 10, plus the kinetic energy at 10. And look, I'll put a little 20 right here. And then I go through and I solve for what is the velocity at 10 centimeters. And so I have 1/2. I'm going to go and put in some numbers here. K was 1200.2 meters squared. I lose the negative because it's squared anyway, so it'd go away anyway. You can leave it if you want. 1/2 K 1200 times 0.1 squared plus 1/2 1 kilogram v squared. And then I would solve that for v. And v turns out to be 6 meters per second. Alright, which is less than this. It should be less than this, right? Because the object has its maximum speed here at this point. 6 meters per second. Double check I've done that right. Yep, 6 meters per second. Okay. Hi folks, one more thing in this chapter is power. Power is the rate at which energy is transferred or that work is done. So we can write power, the expression for power, is use a capital P. That's a P. I usually put a base on my P's. Is going to be work over time, or you might see it as energy over time. That could also be power, work or energy over time. The unit, do y'all know what is the unit for power? But that never gets old. Watt is the unit for power. Yes, the watt. Did y'all get that? You didn't get that, did you? That was a joke. 1 watt. It's named after a person, so it's capitalized. 1 watt is equal to 1 joule per second. Right, it's energy per time. And the basic SI units for that are 1 kilogram meter squared per second cubed. All right, you'll do work, energy. You do 1/2 mv squared over time. I'll do that for you. If I really wanted to know what the basic SI units were, I would say 1/2 mv squared. That's energy over time. And then I would say kilogram meter squared per second squared. And then I have another time over there, 1 over seconds. Gives me that cube term. Okay? So that's power. It comes up in your OpenStax assignment that's due on Tuesday. And then it also, we'll have some more clicker questions about it. Let's do those now. So a box is sliding on a frictionless flat surface, runs into a fixed spring, and it compresses the spring by X. If you double the speed of the box, how much would the spring compress then? So I'm taking kinetic energy, and I'm transferring it into elastic potential energy. Remember that kinetic energy, that's that 1/2 mv squared term. And the elastic potential energy, that's the kx, 1/2 kx squared term. If you double the speed, what happens to x? All right, let's stop at 125. Just a few more seconds. Just guess if you're not sure. All right. Put D. D is right. Let me show you. Whenever you encounter these, you want to write down the equations, and then you can think about how the variables change. I know that I have kinetic energy. That's right here. All that kinetic energy is going into potential energy. That's right here. And now I think about what happens if I double these various terms. So if I double that, I get a factor of 4 over here because it's squared. But then if I double this, I also get a factor of 4. So whatever I do to the speed, I'll also do to the compression. I know that it's a little confusing because you have the squared term, but you also have a squared term here. So it's like they sort of cancel one another out. So the answer is B. There's a picture missing here. Let me see if I can remember which it is. Do y'all have it in your... No. Paul is going down a slide that looks like this. This is Paul. Kathleen, on the other hand, she's going down a slide that looks like this. I call her Katie. All right? Whose velocity is greater at the bottom? This is a frictionless water slide, but it has different shapes. All right, let's stop at 1 minute. C is right. They'll both have the same speed. I know what you're thinking with Katie. It's frictionless, folks, right? There's no friction on this. Now, Katie would be going faster if there was friction, but it's all about the energy. I have potential energy at the top. All of that goes into kinetic energy. It all goes into kinetic energy because there's no friction. There's no non-conservative forces. So C is the right answer here. All right? What time is it? Time to go? Yeah, we'll wrap this up, okay? Have a great day. Have a good weekend.